on this example, we want to use the given 0 to find the remaining zeros of the function. The function we're working with is h of x equals 3x to the 5th plus 5x to the 4th plus 138x cubed plus 230x squared minus 441x minus 735. We are given one zero to be negative 7i. So this function is a polynomial function with real coefficients. And because it's a polynomial with real coefficients, we can use the conjugate pairs theorem. When we have a complex zero, like negative 7i, the conjugate pairs theorem said we also have the conjugate of this as another zero. So we know a second zero to be 7i. 7i is the conjugate of negative 7i. We also know that when we have a zero of a polynomial, we can identify a factor of that polynomial. So with a zero of negative 7i, we have a factor of x minus that zero. So x minus negative 7i is x plus 7i. We also have a zero of 7i, which means that we have a factor of x minus 7i. So my strategy for finding the remaining zeros is going to be to divide out the factors that I already know are within this polynomial. I can do them individually, or I can do them combined together. And I'm going to combine them together because that means a little bit less long division. So I'm going to multiply these two conjugates together, x plus 7i times x minus 7i. And it has the added bonus that when you multiply them, when you multiply conjugates together, the i's will go away and we won't have to deal with complex numbers when we do our long division. So that gives us x squared minus 7ix plus 7ix plus, nope, that's a minus 49i squared. In the middle, these two terms have opposite signs and they're going to cancel each other out. And I squared is defined to be negative 1. We get x squared plus 49. And we're going to divide these two factors out of our polynomial. And hopefully when we divide that out, we'll be able to either factor or use the rational zeros theorem to find the remaining zeros that we have. So I'm going to divide x squared plus 49 into 3x to the 5th plus 5x to the 4th plus 138x cubed plus 230x squared minus 441x minus 735. This is a long one. Okay, so when you do this long division, you start off by focusing just on the leading terms. And I'm thinking, what can I multiply x squared by to get 3x to the 5th? So that's going to be 3x cubed. 3x cubed times x squared is 3x to the 5th. 3x cubed times 49, let's see, 49 times 3 would be 147. So we have a plus 147x cubed. And with long division on this step, you subtract. It eliminates that leading term. 3x to the fifth minus 3x to the fifth is 0. That's why we focus on that leading term. And 138 minus 147 gives me a negative 9x cubed. The rest of the terms I'm just going to carry down. So then we repeat that process over again. And I'm going to focus now on the leading term here and the leading term here. I want to think, what can I multiply times x squared to get 5x to the fourth? And that would be 5x squared. So that's what goes up here, 5x squared. We'll multiply. 5x squared times x squared is 5x to the fourth. 5x squared times 49 is 245x squared. 245x squared. So I'm lining it up with the x squared term so I can combine like terms. And I'm going to subtract. We change the signs and subtract. So 5x to the fourth minus 5x to the fourth cancels out that leading term. And I'm carrying down the cube term. 230 minus 245 is a negative 15x squared, and I'll bring down the rest of these terms. Minus 441x minus 735. Now we repeat that process over again, focusing on the leading term here and the leading term here. What can I multiply by x squared to get negative 9x cubed? And that would be a negative 9x. Negative 9x times x squared is negative 9x cubed. Negative 9x times 49 would be 441. And that would be a negative 441x. Let me just double check my math. 49 times 9 is 441. Okay. And we change our signs. And that's going to cancel out the leading term. Negative 9x cubed plus 9x cubed cancels out. We'll carry down the negative 15x squared. Negative 441x plus 441x cancels out. And I'll carry down the minus 735. So we've got to repeat that process over again. Let's see, we'll use this color. We want to match this leading term with this leading term. And what can we multiply by x squared to get negative 15x squared? That would be a negative 15. Negative 15 times x squared is a negative 15x squared. And negative 15 times 49 is 735. So we have a negative 735. We are going to subtract, changing these signs, and we get that leading term canceling out. And as we expected, we get a remainder of 0. We knew we'd get a remainder of 0 because we knew these were both factors of the polynomial. So we know that h of x is x squared plus 49 times what we got at the top there, 3x cubed plus 5x squared minus 9x minus 15. So from here, we now want to try to figure out what are the zeros of our polynomial here, of this portion of the cubic. Sometimes we get lucky and it's something that factors nice, and I think this one might factor nice, so let's give it a try. 3x cubed plus 5x squared minus 9x minus 15. And I'm going to use a method called grouping. I'm going to group two terms at a time together and take the greatest common factor out of each group. So for that first term, or first pair, we have x squared in common, and we're left with 3x plus 5. And for the second group, I'm going to factor a negative and also a 3. And when I factor that out, I'm left with 3x plus 5 as well. So with that grouping method, we need for these parentheses to match each other in order for the grouping method to work. So we can factor out that common factor of 3x plus 5, and we're left with x squared minus 3. And now that it's in this factor form, I'm going to be able to identify the remaining zeros by setting these factors equal to 0. So I'll set 3x plus 5 equal to 0. Subtracting 5, 3x equals negative 5. Divide by 3, and I have x equals negative 5/3. And if I set the factor x squared minus 3 equals 0, I'm going to add 3 and get x squared equals 3. Square root both sides, and get x equals plus and minus square root of 3. So we've now identified the remaining zeros of this polynomial function. So just to recap, we were given a 0 of negative 7i. We used the conjugate pairs theorem to say that we have a 0 of 7i. Then we divided the related factors out of the polynomial, and we were able to factor and set those factors equal to 0 to get zeros of negative 5/3, square root of 3, and negative square root of 3. In this question, we want to solve the system of equations. If the system has no solution, say that it's inconsistent. Graph the lines of the system. So in this example, we're going to try to use the graph to help us find the solution. And a couple things that I want to point out that makes this question a little bit more challenging is that we don't have nice numbers that are going to divide easily. And you'll notice that the tick marks that we have here are broken up into quarters. So we may be using a little bit of decimals and fractions to be able to graph these. So I'm going to start with the first equation, 15x minus 6y equals 6. And to solve this, I'm going to write this in slope-intercept form. So I'm going to subtract 15x on both sides. That gives me negative 6y equals negative 15x plus 6. I'll divide by negative 6. And this gives y equals, let's reduce 15 over 6. So 3 goes into 15. 5 times 3 goes into 6. 2 times. We've got 5 over 2x minus 1. So this linear equation has a slope of 5 halves and a y-intercept of negative 1. So in order to graph this line, I'm going to plot the y-intercept at 0, negative 1. And I'll use my slope to get to another point on the line. I'm going to rise 5. And when you rise 5, and run 2. It doesn't matter which size units you use as long as you're consistent with the y and the x, what size. If I can go up 5, 1, 2, 3, 4, 5, and over 2, and that gets me to the next point on the line. So I went up by quarters and moved over by quarters to get to that point. I could have moved up by halves, 5, and over by halves, 2. Now the second equation is 11x plus 4y equals 3. I'm going to solve for y by subtracting 11x on both sides. That's 4y equals negative 11x plus 3, and I'll divide by 4. And this gives y equals negative 11 over 4x plus 3/4. So my y-intercept is 3 over 4, and my slope is negative 11 over 4. I'm going to plot 3/4 for my y-intercept, which is here. So I went 3 units of the 4 whole units. And I want to rise negative 11 and run 4. So I'm going to go down 11. And over 4. And that would be here. I'm going to count that one more time to make sure I'm correct. I've got my mouse here. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 over 4. Okay, and we'll connect those two with a straight line. And it looks like we have an intersection point here. But let me try to draw my line a little bit better. Let's try to be right in the center of that one. And right in the center here. See if that gives us a little bit better. It's going to be hard to tell what the intersection point is if it doesn't fall right on a grid line. So we've got this intersection point here, which will be the solution to the system. However, it's not really falling on a grid line, so it makes it hard to identify what that solution is from the graph. So let's try to find the system algebraically instead. So we could make a guess about that solution, but rather than guessing an approximation, I want to find the exact solution by solving this system. So I've got 15x minus 6y equals 6, 11x plus 4y equals 3. And I'm going to solve using the elimination method. The y coefficients are smaller numbers, so I'm going to use the y variable to eliminate. In order to eliminate, I need to have the same coefficient with the opposite sign. So I'm going to choose 12, which is the least common multiple of 6 and 4. So I need to multiply the first equation by 2 and the second equation by 3. This will give me a new system of 30x minus 12y equals 12. 33x plus 12y equals 9. I'm going to add these equations together to get 63x equals 31. Going to divide both sides by 63. And get x equals 31 over 63. So that gives me the x coordinate of my solution. Then I'm going to get the y coordinate. And we've solved for y on both of these equations up here, so we can use either one of these. So y is equal to 5/2 times 31 over 63 minus 1. So that would give me 5 times 31 . It's 155. 2 times 63, that would be 126 minus 1. 155 over 126 minus 126 over 126. We give 29 over 126. So our solution is the ordered pair 31 over 63 and 29 over 126. So I can see these numbers were a little bit funky, so I went back and checked my arithmetic. And right here I have 12 plus 9, and I wrote 31, and it should have been 21. So this should be a 21. 21 over 63 reduces down. 7 goes into 21 3 times, and 7 goes into 63 9 times, and then that reduces down to 1/3. So that means I can change this kind of messy number here to 1/3. And let me go ahead and erase all this. We have 5 over 6 minus 1. That's 5 over 6 minus 6 over 6. And 5, 6 minus 6 over 6 would give me negative 1/6. And now we have our solution being 1/3 and negative 1/6. And based on that placement, the placement of our solution there, that matches it pretty closely. This line right here represents 0.25. So we're a little bit to the right of 0.25. That's 1/3, 0.3333, repeating. And negative 1/6 is just below the x-axis. So we have our exact solution. So this question says to use the principle of mathematical induction to show that the following statement is true for all natural numbers n. Our statement is x plus 6 plus 24 plus ... plus 8n is 4n times n plus 1. Now, to prove this with mathematical induction means that we have to prove 2 parts. We have our first condition, which is that it is true for n equals 1, the first natural number. And then we have to prove an if-then statement. We have to prove that if it is true for some k, then it is true for k plus 1. So that's the process that we need to go through. You guys are going to be answering this question in my math lab. And because we're answering it in my math lab, they have a very structured way of having you walk through the process. So I took some screenshots of the process in my math lab so that we can make sure that we understand each part of the process. If we were doing this on our own, we could kind of navigate this with a little bit more flexibility, but because we're doing it in my math lab, we have to follow their process. So this is the first question that comes up with this problem. What two conditions must the given statement satisfy to prove that it is true for all natural numbers? So what we're looking for is the two things that I've listed on the right up here. We need to prove that it's true for n equals 1, and that if it's true for k, then it's true for k plus 1. So these are the statements that we were given, and we want to select all that apply. So the first possibility is that the statement is true for the natural number 1. Now that matches our first condition, so we would select this statement right here. The statement is true for any two natural numbers, k and k plus 1. Now that has k and k plus 1 like the second statement, but it's not worded as an if-then statement, so that's not the one that we want. The third statement here says, if the statement is true for the natural number 1, it is also true for the next natural number 2. Now that is an if-then statement, but it doesn't use generic values for k and k plus 1, so that's not the one that we want. This last statement here, if the statement is true for some natural number k, it's also true for the natural number k plus 1. This is the statement that we were looking for. These are the two conditions of mathematical induction that tell us that our statement will be true for all natural numbers n. Okay, so that's making sure that we know how the process of mathematical induction should go. Prove those two conditions. So the next part is that we want to show that the first of these conditions is true. So we want to prove this first condition, that our statement is true for the natural number 1. So what that means is that we want to take our statement right here and prove that it's true for the natural number 1, so by plugging in a 1 into this statement. So here's our statement, and we want to fill in the blank on the left of the equal sign, and we want to fill in the blank on the right of our equal sign. Now, for the natural number 1, we're talking about just one term of our whole sequence being added up. So for n equals 1, we're really just talking about that first one, and you can tell if I plug a 1 into here, 8 times 1 would give me 8. So it's an 8 on the left-hand side. On the right-hand side, we want to take this expression and let n equals 1. That would be 4 times 1 times 1 plus 1. 4 times 1 is 4, 1 plus 1 is 2, 4 times 2 is 8. So we would also fill in an 8 on the right-hand side. So what we've done is we've shown that for n equals 1, the left-hand side is equal to the right-hand side. So we have that first condition met. First condition of the principle of mathematical induction. So then we're going to move on to the second condition. And the second condition, remember, is an if-then statement. And because it's got two different parts, the if part that we assume and the then part that we try to prove, it's sometimes helpful to write down what statements we're given and what statements we're trying to prove. So this right here is the next part, and it says to show that the second condition is satisfied, we're going to write the given statement for k plus 1. So what we're doing here is we're just trying to envision the then part of this condition. The second part that we're trying to prove. We don't know if it's true yet, but we're trying to prove it, and we want to know what it looks like before we try to prove it. So let me bring this down. I'm bringing this down because it's helpful if you see where it starts to know where it goes. So we want to write our statement for k plus 1, and what that means on the left-hand side is that we need to go one term further. We've gone to the kth term. This is where the kth term is. We want to go k plus 1, so we're going to plug k plus 1 in. So we get 8 times k plus 1. On the right-hand side, we're going to change this n to k plus 1 because we're going all the way to k plus 1, that changes our value in the formula. So that's going to be 4 times k plus 1 times k plus 1 plus 1. That's 4 times k plus 1 times k plus 2. Notice it says to leave it in factored form. Let me get the next part here. Now this is going to be just a little drop-down menu to select the correct statement. If the statement is true, if the statement for k plus 1 is true whenever it is true for k, the statement will be true for all natural numbers. Okay, so the next part says use the statement for k to simplify the left-hand side. So this is a little bit confusing because it's wanting you to use what you did a few parts back to get this right here. So we wrote this out for k plus 1 on the left-hand side, and I want to work my way to the right-hand side over here. So I'm starting off with the left-hand side over here. This is 8 plus 16 plus ... plus 8k plus 8 times k plus 1. And then I'm going to take this statement for k and make a substitution. So I can change this part right here and turn it into the other side of the equation. So that becomes 4k times k plus 1 plus 8 times k plus 1. And then I'm trying to take a look at what they have already. They have a blank, and they have some stuff written out already. So in the blank, I'm trying to figure out, I've already got k and k plus 1, so in the blank I need to put just the 4, so just this part right here. And I already have the k plus 1, so in the blank needs to go the 8 here. Okay, so then the next part that they want us to do is to use the distributive and associative rule to rewrite the right-hand side. So the right-hand side here, so I think what they want us to do is to take the right-hand side of this, because remember, we're trying to make sure these two sides are equal. This side was our left-hand side that we simplified. And now we're going to work on the right-hand side, and hopefully we can get it to match so that the two are equal to each other. That's the question mark. Are they equal to each other? So if we take the 4 times k plus 1 times k plus 2, and it says to use the distributive and associative rules, and I'm trying to take a look at what they have right here to decide how I'm going to work out the math. So they have the k plus 1 there, and so I don't want to do anything with this k plus 1. What I want to do is distribute that. So we're going to distribute so that we take this, I guess we're going the other way. We're distributing the k plus 1 to each of these parts. So if we distribute that, we would have 4 times k plus 1, and 4 times 2 times k plus 1. And that's 4k times k plus 1 plus 8 times k plus 1. So now I can see that the 4 is what they want in the blank, and the 8 is what they want in the blank. Because I've got k times k plus 1, k times k plus 1. The only thing that's not written down is the 4. And here I just have the k plus 1, and the only thing written down, not written down, is the 8. So the next part is where we're finalizing our statement. So use this to draw a conclusion regarding the given statement. And it gives us 3 options to choose from. So these are the options that it gives us. And it says, since the right side of the statement for k plus 1 simplifies to the left side of the statement for k, the second condition required to prove that the given statement is true for all natural numbers is satisfied. So this is not correct because we have the left-hand side for k plus 1 simplifying to the right-hand side for k plus 1. So it's not that it's k and k plus 1. The second statement says, Since this statement cannot be shown, well, that's not true because we did show it. We showed that the two sides were equal to each other, and this final option is the only one that makes sense. Since this statement is true for all values of k, the second condition required to prove the given statement is true for all natural numbers is satisfied. So all of that is saying that we proved the second condition. So since we proved the second condition and we proved the first condition, we have shown, using mathematical induction, that the statement is true for all natural numbers. So we have shown that 8 plus 16 plus 24 plus ... plus 8n is 4 times n times n plus 1 for all values of n. So on this question, we want to use the principle of mathematical induction to show that the given statement is true for all natural numbers n. The statement we're trying to prove this time is 1 plus 3 squared plus ... plus 3 to the n minus 1 is equal to 1/2 3 to the n minus 1. Now, in order to prove this, we need to use mathematical induction, which has two conditions. The two conditions are that it is true for n equals 1, the first natural number, and then we need to show that if it is true for some value of k, then it is true for k plus 1. The second condition creates a domino effect that these successive terms are true, and then we have to knock over that first domino by showing that it's true for the very first natural number. Now, once again, we're going to be using my math lab as our homework system for this, and so it's going to force us into solving the problem in a certain way. We'd have a little bit more flexibility if we were doing this without my math lab, but we have to follow their process here. So the very first question that they ask us is, what is the first step in an induction proof? That's mathematical induction. And the first step is to make sure that it is true for n equals 1. So we are going to show that it is true for n equals 1. So here's what the question looks like. To show that it is true for n equals 1, we need to complete these steps. We're going to take the left-hand side of our statement. The left-hand side of our statement is really just one term of the sequence, or one term of the series. So we're going to plug a 1 in for n. And the right-hand side, we're going to plug a 1 in for n. And we'll simplify each side, and if it's true, the two sides should be equal to each other. So we have 3 to the 0 being 1 on the left-hand side. On the right-hand side, we have 1/2 times 3 to the 1 minus 1. That's 1/2 times 3 minus 1. 1/2 of 2, half of 2 is 1. So we also get the right-hand side being 1. So we know that this statement is true for the first natural number 1. So then we need to move on to what is the next step in the induction process, mathematical induction. And the next step is that if it is true for some k, show true for k plus 1. So it's helpful to write down what the statement is we're trying to prove. So this is the statement that we're trying to prove, and that is for k plus 1. So let me show you. We want to see what we were given. This is the original question. And we want to write down what this statement would look like if it were for k plus 1. So this is what we have for k, and we want to go one term more. If we go one term more, that means k increases by 1, so this is 3 to the k on the left. On the right-hand side, we're going to change this n to k plus 1. So that's 1/2 times 3 to the k plus 1 minus 1. According to the principle of mathematical induction, we assume that 1 plus 3 plus 3 squared plus dot 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 plus 3 to the k minus 1 is equal to 1/2 times 3 to the k minus 1. So this part right here is our if-then statement. This is the if, this is what we're saying, and this part right here is then, which is what we have to prove. So then we have to keep proving it. Okay, so to prove it, use this assumption to express the k plus 1 terms on the left-hand side as a single term with a denominator of 2. Okay, so what they mean by this is that they want us to take this left-hand side, and that's 1 plus 3 plus 3 squared plus dot 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 plus 3 to the k minus 1 plus 3 to the k. We're going to use our assumption. We're going to make a substitution. We're going to be able to substitute in for this part. So that becomes 1/2 times 3 to the k minus 1 plus 3 to the k. And we want to try to write it in this way here. To write it in this way would have a 2 in the denominator. Okay, so to write it with a 2 in the denominator means that I need a 2 on both of these terms. So I'm going to write this as 2 over 2 times 2 over 2. 2 over 2 is the same thing as 1, which is why I'm allowed to do that. And now that I have it as the same denominator, I can combine the numerators. So in the numerator, I would have 1 times 3 to the k minus 1 plus 2 times 3 to the k. Let's get rid of those parentheses. That's 3 to the k minus 1 plus 2 times 3 to the k. Now, these two are like terms. We can combine those together. This one has a 1 as a coefficient, and this one has a 2 as a coefficient. And when we combine them, there are 3 like terms. That's 3 times 3 to the k minus 1 over 2. And then using our rules of exponents, these have the same base, and I can add those exponents together to make this 3 to the k plus 1 minus 1 over 2. So up here, we get in the blank 3 to the k plus 1 minus 1. Now, we're almost to the end. We want to know, does this resulting statement show us that it is true for k plus 1? So, remember our statement here. What we want to pay attention to is what we just did the same as our right-hand side of that k plus 1 statement? And they are the same. 1/2 times 3 to the k plus 1 minus 1 is the same as 3 to the k plus 1 minus 1 over 2. So we have just proven that it is true for k plus 1, and that satisfies the second condition of mathematical induction. So we have these statements to choose from here. Yes, because multiplying both sides by 2 and simplifying results in the same expression on both sides. Yes, because evaluating the left-hand side for k equals 1 is the same result obtained above for evaluating the right-hand side when n equals 1. That applies to a totally different thing. No, because you can't. No, we got yes, they're the same. Yes, because when written as a single term, the expression on the left-hand side is the same as on the right-hand side for k plus 1. So, yes, when you write it, the left-hand side and the right-hand side are the same. One final thing that we're going to do this is the very final statement. And a couple of drop-down menus. Since plus me plus 3 squared plus dot plus 3 to the n minus 1 equals 1/2 3 to the n minus 1 satisfies both conditions. The statement is true for all n. Okay, I think I lost my screen. Let's bring it back here. So a couple drop-down menus here. This statement satisfies both conditions, and we have proven that the statement is true for all n. For this one, we want to determine whether CA is defined. If it is defined, express the result as a single matrix. If it's not, say not defined. Now, A is a matrix and C is a matrix, so capital C, capital A written next to each other like this means that we're trying to do matrix multiplication. So in order for us to know whether this matrix multiplication is defined, we have to pay attention to the rows and columns for the first matrix and the second matrix. We want to do CA. In looking at matrix C, it has 3 rows and 2 columns. So we say that it's a 3 by 2 matrix. And then matrix A has 2 rows and 3 columns. So we say it's a 2 by 3 matrix. Now, in order for the matrix multiplication to be defined, we need to look at the columns of the first matrix and the rows of the second matrix. If they're equal to each other, then the matrix multiplication will be defined. So since we have 2 columns in matrix C and 2 rows in matrix A, the matrix multiplication will be defined. And then we know what size matrix we're going to produce. We use the rows from C and the columns from A. So we're going to create a 3 by 3 matrix when we do this multiplication. 3 rows and 3 columns. So in our new matrix, let's say I call this matrix D. This position is D11. That's for row 1, column 1. Then we have D12, D13, D21, that's row 2, column 1, D22, D23, D31, D32, and D33. We're going to have to do 9 calculations for this matrix because it's a 3 by 3 matrix. So when we're figuring out D11, we're going to use row 1 of matrix C and column 1 of matrix A. So to get D11, we're going to do 5 times 0 plus 1 times 1. That's 5. 5 times 0 is 0. 0 plus 1 is 1. So this is going to be a 1. Let me write it over here. We're going to have a 1 in row 1, column 1. And D12, that is row 1, column 2. We're going to use row 1 of C and column 2 of A. So that's 5 times 4 plus 1 times 5. That's 20 plus 5 is 25. 25 in row 1, column 2. So then we're going to do row 1, column 3. And in row 1, column 3, we need to use row 1 of C, column 3 of A. So we're going to do 5 times negative 3 plus 1 times 3. It's negative 15 plus 3, which is negative 12. Negative 12 in row 1, column 3. We're going to continue on to row 2, column 1. We're going to use row 2 of C, column 1 of A. So D21 would be 6 times 0 plus 5 times 1. That works out to be 0 plus 5, which is 5. We get a 5. 5 in row 2, column 1. Now we'll do row 2, column 2. And we need to use row 2 and column 2. So that's 6 times 4 plus 5 times 5. And that will give us 24 plus 25, which is 49. So 49 in row 2, column 2. Then we'll do D23. That's row 2, column 3. So we're finding this position here. We're going to use row 2 again and column 3. So that'll be 6 times negative 3 plus 5 times 3. We have negative 18 plus 15, which is negative 3. So then we want to move on to row 3, column 1. So row 3, column 1, we'll use row 3 of C, column 1 of A. That would give negative 6 times 0 plus 5 times 1. That's 5. We want to find row 3, column 2. We use row 3 of C, column 2 of A. That's D32. Negative 6 times 4 plus 5 times 5. We get negative 24 plus 25 is 1. Final calculation, D33. We need to use row 3 of C and column 3 of A. So that would be negative 6 times negative 3 plus 5 times 3. So that's 18 plus 15, and that would be a 33. So we've done the matrix multiplication. Okay, so we've got the answer, but there's a lot of arithmetic involved there, so I'd like to check my work. So I'm going to use my TI calculator. And what I need to do is enter matrix A and matrix C. So I'm going to go to second. X to the negative 1 takes me to the matrix menu in the calculator. And I'm going to go over and edit matrix A. Matrix A has 2 rows and 3 columns and is 0, 4, negative 3, 1, 5, and 3. And let's go back to that matrix menu and let's edit matrix C. And matrix C has 3 rows and 2 columns. And it is, I'm not sure if I can read that all that well. It looks like a 5, 1, 6, 5, negative 6, 5. Let me just verify. Yeah, that's a 5. We have 5, 1, 6, 5, negative 6, 5. Okay, so now I've entered those matrices in, and I want to perform the matrix multiplication, so I'll go to second. X to the negative 1 takes me to the matrix menu, and I want to select matrix C. And then let's go back to that matrix menu, select matrix A. Now I'm doing C times A, and it has done the calculation for me. 1, 25, negative 12, 5, 49, negative 3, 5, 1, 33. So we did all of our arithmetic correctly. The cross-section of a nuclear power plant's cooling tower is in the shape of a hyperbola. Suppose that the tower has a base diameter of 216 meters and a diameter at its narrowest point of 40 meters above the ground. It's 72 meters. If the diameter at the top of the tower is 144 meters, how tall is the tower? Okay, so when I read this the first time, I'm having a little bit of trouble visualizing a picture for it, because we need to be able to put these numbers towards the picture. So I want to remind you what a hyperbola is going to look like. Hyperbola, if it has a vertical orientation, will look something like this. And if it has a horizontal orientation, will look like this. So we want to visualize what that tower looks like. And remember that the tower is going to be three-dimensional, but we're only looking at a cross-section of that tower. So let's see. Here's what I'm imagining the tower to look like. Something like this. So I'm imagining the cross-section of the tower to be a parabola that's oriented horizontally. Okay, so I'm imagining this horizontal orientation, and now that we're imagining the orientation, let's see if we can put some of this, some of these numbers towards the picture. So it says, suppose the tower has a base diameter of 216, the base diameter of 216, and a diameter at its narrowest point. So at the narrowest point would be here, the diameter is 72, and this is a distance of 40. The diameter at the top of the tower is 144. How tall is the tower? So that is the diameter at this point here, 144. Okay, so that was very helpful to get a picture. So some reminders is we do have an equation of a hyperbola, and we're going to center our hyperbola at 0, 0 so that the equation has its simplest format. And what that means is that right here in the middle, Right here in the middle is our center at 0, 0. And it'll have that equation x squared over a squared minus y squared over b squared equals 1. And we need to remind ourselves what that a and b stands for. So that a is the distance from the center to the vertex, and b is going to help us define the slope of our asymptotes. The asymptotes crisscross across the center right at the origin, and so this 216 and 40 will help us, actually the 72 and the 40 will help us figure out that value of b. So using that 72 is going to be the distance from vertex to vertex. So if we cut that in half, that means that the value of a will be 36. Okay, so that helps us as well. Then we need to find the value of b and c so that we can figure out how tall the tower is. So we already know that this is 40. Let's see how we can find the next piece of information. Okay, so now what I'm going to do is use some of this other information to get the value of b. So this 216 that we were given is, if you'll recall, the diameter at the base. So since we made the choice, I'm going to draw my picture a little bit bigger for us. It'll be helpful. So since we made the choice to make our center at 0, 0, that means that this base is at negative 40. So we said right here that 40 meters above the ground, we have a diameter of 72. So we had this diameter of 72, which was 40 meters above the ground. So this is 40. And the diameter at the base is 216. So if I cut that in half, if I cut the 216 in half, that is 108. That tells me these ordered pairs right here are going to be 108, comma, negative 40, and negative 108, comma, negative 40. So these are ordered pairs that have to be on this equation here. So they have to make it true for the x and the y. And we already know the value of a, so I can use that to solve for b. So we have x squared over a squared minus y squared over b squared equals 1. Let's choose one of these points. So that would give me 108 squared over 36 squared minus negative 40 squared over b squared equals 1. 108 squared, a really big number, 11,664 over 36 squared is 1296. Let's see if that comes out nice. 11,664 divided by 1,296. It's a very nice number, 9. 40 squared is 1600 over b squared equals 1. So we have 9 minus 1600 over b squared equals 1. I'm going to subtract 9 on both sides. That gives negative 1600 over b squared equals negative 8. I'll multiply both sides by b squared. That gives negative 1600 equals negative 8b squared. We'll divide both sides by negative 8 to get b squared equals 200. And I'll square root both sides. And b is equal to let's write it out. Let's see. 2 times 100, square root of 100 is 10. So b is 10 square root of 2. Okay, so now we know the equation of our hyperbola. Our equation is x squared over 36 squared minus y squared over 10 square root of 2 squared equals 1. And we want to know the height of the tower when the top of the tower has a diameter of 144. So this top has got a diameter of 144. And let's see, half of that, half of 144 would be 72. So how can I get this last little bit of information? Let's see. I'm going to think for just a second. Okay, so now that I've thought about it a little bit more, I'm going to be able to write down what the x-coordinates are of these points, and I'll be able to solve for the y-coordinate. So I'm going to have an x-coordinate of 72, which is half of the 144. We're going to plug that in to the equation and solve for y. So that's 72 squared over 36 squared minus y squared over 10 square root of 2 squared equals 1. 72 squared is 5,184. We already saw that 36 squared is 1296. 10 squared to 2 squared, that is 200. And the 5,184 divided by 1296 works out to 4. And I'll subtract 4 on both sides. That gives negative y squared over 200 equals negative 3. I'm going to multiply both sides by 200 to get negative y squared equals negative 600. And divide both sides by negative 1, and y squared equals 600. We have y equals the square root of 600. So this is 10 square root of 6. And looking back on our picture here, that gives us our y coordinate. But if you'll recall, this center point is 40 above the ground, so we need to add in that 40. So we do 40 plus the 10 square root of 6. 40 plus 10 square root of 6 is the height of the tower. Thank you for checking out my videos. Have a great day.